Hello learners, myself Subhasis Maji, professor in Mechanical Engineering of School of Engineering and Technology of Indira Gandhi National Open University, discussing the topic that is energy transfer. This is the second unit of module 1. In the first unit of module 1, we have discussed about fundamental concepts and definitions. There we have introduced the course that is thermodynamics. We have discussed what is thermodynamics and the definitions of certain very important terms like controlled system and control mass and control volume, and some important properties like pressure, volume and so on. And we have also introduced the types of the properties like intensive and extensive properties. So we also introduced the term that is energy. So now in this model we will confine ourselves with energy transfer. So thermodynamics we have already discussed, that is thermodynamics is the science of the relationship between heat, work and the properties of substance. Heat and work are intimately connected through energy, and hence thermodynamics is defined as the study of energy. Energy is essential and vital component of our life, hence knowledge of thermodynamics is essential for all of us. As you all know that thermodynamics deals with stored energy like chemical, potential, nuclear, etc. Energy fluxes like solar, wind, hydro, etc. Energy exchanges like heat and work, and the associated changes in properties. Now when you talk about the stored energy, you think of chemical energy like petroleum we use in our car, and when the fuel burns, then the car moves. That means we are converting. This is the conversions of chemical energy to the kinetic energy. And potential energy also we can say it's the stored energy. Say for example that when water is there at a high altitude or on the top of the hill, so we can use the water turbine, that is hydroelectric plant. That stored energy, since it is at a height, so when it falls from a height h, so we can get this potential energy mgh, and that will convert to kinetic energy, and that kinetic energy we can use for rotating the blades of the turbine, and we can convert that kinetic energy due to rotation to electrical energy that we can use in that hydroelectric plant. And that solar and wind and hydro, these are the energy fluxes, examples for energy fluxes, and energy exchanges like heat and work and the associated changes in properties. Now these are the examples, the different forms of energy. Say for example, when that different forms of energy, you see that when we supply heat and that your ice cream melts, so it is the conversion from heat energy to other form of energy. And you see that forms of energy, that nuclear energy, if you think of nuclear energy, that is that fission and fusion. And for the fission at the earth crust, that nuclear reaction is known as fusion, and for solar energy, that is the fission energy. Now these are the different forms of energy. Internal energy, that is internal energy U, is intimately related to the internal structure of the substance in terms of the internal microscopic energy mode. And we will see that internal energy is a function of temperature. So U is a function of temperature. If the temperature of the gas increases, then definitely the internal energy will increase. So we will talk about internal energy in detail in our subsequent lectures. Now when you think of the law of conservation of energy, that we all know that energy cannot be created nor destroyed. Total energy is always conserved. So the law of conservation of energy, we can also say like this, that the energy of a system remains constant if the system is isolated from its surroundings as regards heat and work. Now, energy and energy transfer. Now that we have defined a system and can describe the state of that system by some set of its properties, we can discuss the quantity called energy. The total energy contained within the system boundary can be given the symbol capital E and is made up of the kinetic energy, potential energy and the internal energy U. So when you think of the total energy, that is capital E, is the sum of kinetic energy plus potential energy and the internal energy U. You all know that kinetic energy is expressed as half mv square, where m is the mass of the object and v is the velocity, and potential energy is expressed as mgz, where m is the mass, g is the acceleration due to gravity, and z is the datum height, and u is the internal energy. Now this is the total energy in terms of kinetic energy because of the motion, and potential energy because of the elevations, and U is the internal energy. Now the intensive form for the total energy, that is small e, that is the total energy by mass, is equal to kinetic energy by mass plus potential energy by mass plus internal energy by mass. So total kinetic energy is half mv square. If you divide by mass, it will be only half v square. Then total potential energy is mgz. If you divide by mass, we get gz, and when you divide capital U by mass, we shall put it at small u. So small u is the intensive property and capital U is the extensive properties. So here you see we can calculate the total energy, that is kinetic energy plus potential energy plus internal energy. We can all, once you get the total energy, so we can calculate small e, that is energy per unit mass. So we can calculate the total energy as well as we can also calculate the small e, that is the intensive form for the total energy. Now here it's a very nice example for the conversion of kinetic energy into potential energy. Say there is a small hilltop where a boy is cycling. So here you see that with a tremendous speed it is coming, and after that he is with that energy, he is just reaching on the top of the hill. Here you see that initially he was having kinetic energy, but when he is just reaching at the top of the hill, its velocity is 0. But that means the kinetic energy becomes 0. But where is this energy goes? And here there is a conversion from kinetic energy into potential energy. And again, when it is going down, that velocity is gaining, and when it is just going down, its velocity increases. That means the potential energy is converting into the kinetic energy. So this is a good example how we are converting the transform from kinetic energy to potential energy, and again from potential energy into kinetic energy. Now energy transfer. To change the value of the system energy E, we must examine a system that is not isolated from its surroundings. How can energy be changed for the system? Note that energy crossing the system boundary could be categorized in many ways and allow the engineer or scientist to easily tie the results of calculation to the performance of equipment such as turbines, compressors and heat engines. Now we will introduce the term work. For thermodynamic work, we can express W is integral of P dV, and this expression is coming from the fact that we know that work is equal to force into distance. So if you divide force by area and multiply again that distance into area, obviously force per area comes out to be pressure, and area into distance comes out to be volume. So when you think of a piston cylinder case or arrangement, then the thermodynamic work done can be expressed as W is equal to integral of P dV, where P is the pressure and dV is the small change in volume. Now there is a sign convention. Sign convention says that the work done by the system is positive and work done onto the system is negative. So we will use this sign convention system, that is work done by the system is positive and work done onto the system is negative. Say for example, when you compress the air, that means we are doing the work onto the system, so that is negative, and when the work is done by the system, that is positive. Now here we will discuss about the constant pressure process. So what should be the final expression for the constant pressure process? We know that work done, the best formula for work done is equal to integral of P dV, but here the limit for the integral is 1 to 2. That means the change of state takes place from the state 1 to state 2. Now since it is a constant pressure process, so work done is equal to integral of P dV, but since it is a constant pressure, so P we can take out from the integral, so it will be P integral of 1 to 2, that is dV, and dV integral of dV is equal to V2 minus V1. So finally we are getting P1 into V capital V2 minus V1, and if M is the mass, then we can write in terms of the specific volume, that is V2 is the specific volume and V1 is the specific volume of the substance at state 1. So final expressions will be P1 into M within bracket V2 minus V1. So this is the expressions for the constant pressure process. Now we see physically how we understand the constant pressure process, because here you see that water is placed in a piston cylinder arrangement, and if you supply heat, the piston will move up because pressure is increasing, and here the volume is moving up. So here this is the constant pressure process, and initially the piston was at an equilibrium positions. Piston and mass and piston is at the equilibrium position, and there is a pressure. When we supply heat, the pressure increases and the piston cylinder will also increase. So this is the examples of constant pressure process, and this is the initial state and other one is the final state. Now see, there is a process that is we call it the constant volume process. So what will be the work done for a constant volume process? So we begin with the expression for the work done is equal to integral of P dV, but it is a constant volume process. That means there is no change in the volume, so there is no work done. So it is if the process is a constant volume process, so net work done is 0 because volume is not changing at all. So next is the hyperbolic process, which is expressed as PV is equal to constant. So here we can also say it is an isothermal process, temperature is constant. So how to calculate the work done for hyperbolic process or isothermal process when PV is equal to constant? So you see that if PV is equal to constant, so pressure is equal to constant by volume. If you put the value of P, that is constant by volume, in the main expressions, so the main expressions for W will be equal to integral 1 to 2 P right constant by V. So it is dV by V, and dV by V is nothing but log 2 by V1. So final expressions we will get P1 V1 ln, that is log V2 by V1, where V2 is the final volume, V1 is the initial volume. So this is the expression for the work done for hyperbolic process where temperature remains constant. Now this is a very important point, that is the polytropic process. In polytropic process is expressed as PV to the power n is equal to constant. So again we can do it with little bit algebra. So if PV to the power n is constant, so P is equal to constant divided by V to the power n. So put the value of P, that is constant, divided by V to the power n in the expression for the work done, and after little bit algebra we can calculate the final expression for W is equal to P1 V1 minus P2 V2 whole divided by n minus 1, where n is the index. And if you write down these expressions in terms of specific volume, that is m within bracket P1 small v1 minus P2 small v2 whole divided by n minus 1. Now there is a very important process, we call it adiabatic process. In adiabatic process there is no heat transfer from system to surroundings. In that case the gas is confined within the piston cylinder, and the piston as well as the cylinder is thermally insulated. So there is no possibility for heat transfer from system to the surroundings. And at state A1 there is P1 pressure, V1 volume, and T1 is the temperature, and the final state at state 2 the pressure is P2, volume is V2, and temperature is T2. So we in adiabatic process we write down PV to the power gamma is equal to C. We will use the same formula for which we have already discussed for the polytropic process. So in n only thing n we will take as gamma. Now we talk about the heat. Heat is the interaction between systems which occurs by virtue of their temperature differences when they communicate. So for heat transfer there has to be temperature difference and communication, and sign for heat transfer, that if there is a heat loss from the system we call it negative, and if there is heat gain we call it positive. Three modes of heat transfer, we already know that these three modes of heat transfers are conduction, convection, and radiation. And whenever there is any heat transfer, they will be either through the conductions or convections or radiations. But there may be some cases where all types of heat transfer takes place. So this is the case that a saucepan having some water we are heating in the furnace. So here you see that when you hold the handle of the saucepan, if it is a metallic, then there will be heat transfer through conduction. And here you see that convection process is also takes place in this process, and since we are heating, so because of heat there is a radiation. So this example gives us the three modes of heat transfer simultaneously occurring for a simple case. But in general, when the heat transfer takes place in solid, that is due to the conduction, and when the heat transfer takes place in liquid or gas, that is the convection, and the heat we get from the sun, that is due to the heat transfer due to the radiation. Now energy, that the increase of energy of a system during a process is equal to the net heat minus the net work during the process. So if Q is the heat transfer and W is the work transfer, so change in energy of the system can be defined as Q minus W. Now let us discuss some numericals, and if we can solve this numerical, then whatever we have discussed till now, it will be a crystal clear for you. Now we have already discussed the work done for constant pressure process. We have discussed about the work done for the isothermal process, or we have also discussed about the work done for the polytropic process. Now, whenever you solve any problem, first of all you have to know what process is going on. So this is a very interesting process. You see that find the work done in kilojoule by an ideal gas in going from state A to state C. Here you see that the state A is the initial state, and here temperature is constant, that is PV is equal to constant. So this is an isothermal process where temperature remains constant. So A to B is the isothermal process, and B to C, you see the pressure is constant, that is the constant pressure process. So the part of the work for this process is due to the isothermal process where temperature remains constant, and the remaining part of the work done is the constant pressure process. So here we will see how to calculate the net work done. So net work done, when you calculate, you see that from A to B, it is a temperature, this process temperature remains constant, that is it is an isothermal process, and B to C it is a constant pressure process. But for isothermal process, we know the expression for the work done, that is PV VV ln VV by VA, plus for a constant process the expression for work done is PV within bracket VC minus VV. But what is PV? That is the pressure at the point B. What is VV? That is the pressure at the point B. The pressure at the point B, that is given as 100 kilopascal, and the volume at point B is given 2 meter cube. So these values are known. And ln VV, that is the volume at point B, that is 2 meter cube, and VA is the initial volume, that is given as 3. So all these data are given, so we can very well use this expression for calculating the work done for the isothermal process. But when the process occurs from B to C, it is a constant pressure process. So we know pressure, we know volume at point C and volume at point B. So we can calculate, and final result will be equal to minus 181.10 kilojoule. But one very interesting thing is this, that in these expressions you are getting the final work done as minus, negative. The reason behind this, that this is the work done onto the system. That means it is the compression process. The volume is initial volume was 3 meter cube and final volume of the gas is 1 meter cube. So it is a compression process. So for compression process we have to do work done onto the system, and that is by convention that we are doing work onto the system, that is negative. That's why the final result is coming as negative. So net work done is minus 181.10 kilojoule. Let us discuss this problem, that is example 2. On the surface of the moon, where the local gravity of G is 1.67 meter per second square, 2 kg of a gas occupy a volume of 1 meter cube. Determine the specific volume of the gas in meter cube per kg and density in gram per centimeter cube. The specific volume is volume per unit mass. So volume is given as 1 and mass is given as 2. So the final result will be 0.5 meter cube per kg. That is the specific volume. Density is equal to mass per volume, that is mass is given as 2 and volume is given as 1. So density comes out to be 2 kg per meter cube. But we have to convert this density in the unit of gram per centimeter cube. So if you convert kg to gram, we have to multiply by 1000, and meter cube we have to for 1 meter is equal to 100 centimeter. So meter cube means 100 into 100 into 100 centimeter cube, and that finally it will comes out to be 2 into 10 to the power minus 3 gram per centimeter cube. Now the next problem we have taken as calculate the work done by a body of 15 kg mass falling freely in a vacuum through a vertical distance of 15 meter in a gravitational field of 6 meter per second square. It is a very interesting case that the body is falling freely. So when a body is falling freely, it does no work. So as the body falls freely in a vacuum, there is no interaction across the system boundary, and hence the work done by the body is zero. Of course, there is an exchange of energy between the potential and the kinetic energy mode. So this is another example, that is example 4. A mass of gas is compressed in a fully resistant process from 80 kilopascal and 0.1 meter cube to 0.4 megapascal and 0.03 meter cube. Assuming that the pressure and volume are related by PV to the power n is equal to constant, determine the work done by the gas system. We have already discussed the work done for a polytropic process. We have done the expressions for the work done, that is equal to P1 V1 minus P2 V2 whole divided by n minus 1. But in this case, you see that pressure 1 P1 is given as 80 kilopascal, V1 is given as 0.1 meter cube, that is volume, initial volume. The final pressure P2 is given as 0.4 megapascal and the final volume is given as 0.03 meter cube, but n is not given. So how to calculate n? That is our discussion. So here n is not given, but it is given that this process is a polytropic process. For the polytropic process, we know that P1 V1 to the power n is equal to P2 V2 to the power n. So we know P1, we know V1, we know P2, we know V2, so we can calculate the value of n. You take logarithm on, or if you write down the expression from here, that P1 by P2 we can calculate equal to V2 by V1 whole to the power n, and take logarithm on both sides, you will get the value of n is equal to ln P1 by P2 divided by ln V2 by V1. Now we know P1, that is initial pressure, and we know V1 at the initial volume, we know P2, that the initial pressure, the final pressure P2, we know the final volume V2. We just substitute all these values in this expression, we can calculate the value of n. That comes out to be 1.34, and if you put the value of n in this final expressions, then we can calculate the work done, that is equal to minus 11.76 kilojoule. Again we are getting the value minus because the work is done onto the system, that's why we are getting the final value. Now there are other modes of energy, that is chemical energy, strain energy, electrical energy and magnetic energy. And here you see a very interesting diagram where there is a battery. Through the battery, chemical energy is converted to electrical energy, and that electrical energy is also converting magnetic energy because the current is flowing through a coil. One nail is there inside the coil, and if there is a magnetic flux induced because of the current flowing through the coil, the nail will also be magnetized, and if there is a clip, paper clip, and that clip will be attracted by the magnet. So again it is the case of kinetic energy. So you see that from this diagram there is a chemical energy, conversion of chemical energy to electrical energy, and conversions of electrical energy to magnetic energy, and finally the conversions of magnetic energy to the kinetic energy. So all these things is happening from this diagram. So battery, when it is on, there will be current flowing through the circuit, and current will flow through the coil, and there will be magnetic flux induced, and in turn the nail will be magnetized, and the paper clip will be attracted by the magnet. Now this is a very simple objective type questions. Let us see how we can solve this problem. In which of the following process will the internal energy of a system remains constant? But we all know that for isothermal process, when temperature remains constant, there is no change in internal energy. So the first option is correct. Second one is that 500 gram of ice at 0 degree centigrade is mixed with 540 gram of ice at 0 degree centigrade is mixed with 540 gram of water at 80 degree centigrade, what will be the final temperature? Here you see that when ice melts, it needs heat. So how much heat is required? So for 540 gram of ice, if it melts, then the latent heat of ice is 80 calorie. So it needs heat 540 into 80, and that heat will be required from the 540 gram of water at 80 degree centigrade. But when here heat loss is equal to heat gain, so heat gain by the ice will be equal to the heat loss by the water, and when the water will be converting from 80 degree centigrade to 0 degree centigrade, so the loss of water will be a loss of heat by the water will be 540 into 80. So the final temperature will be only 0 degree centigrade. Only thing, in this process ice will be completely melt into water. And the second question is this, that compared to burn due to air at 100 degree centigrade, a burn due to steam at 100 degree centigrade, which is more, first option is more dangerous and less dangerous and equally dangerous and none of the above. See, the heat contained by the steam at 100 degree centigrade is more than the heat content of air. So compared to burn due to air at 100 degree centigrade will be less dangerous. So more dangerous will be the burn due to steam at 100 degree centigrade. And this is the another objective type question, that in a cyclic process the internal energy of the gas increases, decreases, remains constant, becomes zero. But you know very well, for a cyclic process the properties will not change. So if you think of the internal energy of the gas, that will remain constant. So the internal, in a cyclic process, the internal energy of the gas will remain constant. There will be no increase or decrease of the internal energy for a cyclic process. Now let us summarize what we have discussed in this in today's class. We have discussed about the thermodynamics, we have discussed about the energy, we have discussed about forms of energy, we have also discussed about the transfer of energy by giving suitable examples, and we have also discussed about the thermodynamic work and some numericals. We have discussed about the different processes for calculating the work. If the process is the constant pressure process, for which the expressions for the work done will be different, and if the process is say isothermal process, then the expression for the thermodynamic work done will be different. And also we have discussed about the thermodynamic work for the process which is polytropic process, for which the pressure volume given as PV to the power n is equal to constant. So in the next class we will discuss more numericals, we'll discuss the more and the applications for the first module. So for that, thank you very much. If you have any difficulties, you can ask through mails or through mobile. Thank you very much.